In the last video, we took a look at symmetry about the y-axis. The other two types of symmetry we're going to study are symmetry about the x-axis and then symmetry about the origin. Now here's a graph that has symmetry about the x-axis. So the x-axis sort of serves as a mirror, and the top part of the graph is a mirror image of the bottom, and vice versa. Now, if we've got symmetry about the x-axis, most of the time when we have that, we're going to fail the vertical line test. So I want to remind you, we are not at this point talking exclusively about functions. The only sorts of functions that could have symmetry about the x-axis would be things like y equals 0, which is just the horizontal line that's on the x-axis. There, every point is on the mirror and every point is its mirror image. That's going to have symmetry about the x-axis. The only other functions that would have symmetry about the x-axis would be parts of this line. If this line has as its domain all real numbers, if I said, well, let's just look at the part where x is positive, or just the part where x is between -2 and -3, those would be technically different functions. They would have the same formula, but a different domain. But those are the only sorts of functions that can have symmetry about the x-axis. If I've got a point whose y value is not 0, and I've got a graph that's symmetric about the x-axis, it's not the graph of a function. Because if I've got this symmetry, if I've got a point here, xy, the mirror image point is going to have the same x value, but the opposite y value. So there, if y is not 0, these are two different points. These are two different y values associated with the same x value, and then we would not have symmetry, or then we would not be a function because we would fail the vertical line test. Now, there are plenty of graphs and the equations that give us those graphs that do have this type of symmetry. They're just not graphs of functions. Most of our work is going to be with functions, but occasionally we're going to study things that aren't functions. So this is still an important type of symmetry. And so let's just take a look at an example. Let's say I had x plus y to the 4th equals 7. And I want to know, does this graph exhibit symmetry about the x-axis? So I would suppose that xy is on the graph. And that would tell me that when I plug in those numbers, I get an equation that's true. Okay. And then I would ask, is the mirror image point, x, the opposite of y, on the graph? And so here, I'm going to be replacing y with the opposite of y. So my equation becomes x plus the opposite of y to the 4th equals 7. And I'm just checking to see, does this simplify to this equation that I know is true? If it simplifies to the same equation, then I know that this point is on the graph, and so we have this type of symmetry. If it simplifies to a different equation, then no, this point is not on the graph, it's on a different graph. It's on the graph of the other equation that it simplifies to, and so we would not have this type of symmetry. So this is going to be x plus. Now the shortcut here is that that's an even power. So I'm taking -y times -y times -y times -y 4 times. That's going to give me an even number of negative signs, and they're going to cancel out. So that simplifies to the same equation. So this graph would be symmetric about the x-axis. And it's basically not going to be the graph of a function. Notice that even power of y tells us that we're working with something that is not a function. The third type of symmetry that we can have is symmetry about the origin. That's also called rotational symmetry, and we'll see why in just a moment. A nice example of a function, and this one will be a function, that has this type of symmetry is f of x equals x cubed. And remember, f of x is just a fancy name for y. Now, when we were plotting this, if you remember, the origin was on here, and then we had the point 1, 1, and we also had the point negative 1, negative 1. Well, it turns out those points are mirror image points under this type of symmetry. So the point 1, 1 here would look in the mirror. The mirror now, instead of being an entire line, we're imagining that the mirror is just this individual point. So this point here looks in the mirror, and to see its mirror image, we just continue that line the same distance on the other side of the origin. So 1, 1 sees as its mirror image negative 1, negative 1. And in general, for this type of symmetry, the rule is that if a point xy is on the graph, so is the opposite of x, the opposite of y. So when we're testing for this sort of symmetry, we're going to replace both x with the opposite of x and y with the opposite of y to see whether that new equation simplifies to the original equation. Okay, now I mentioned this is called rotational symmetry. To illustrate that, I can't really use my whiteboard because I don't want to undo all of the duct tape that's attaching it to the wall here. But if you have a piece of paper, here I've graphed y equals x cubed on just a piece of paper. Now if I rotate this and just flip it upside down like that, so I'm rotating it 180 degrees so that I'm turning it upside down, the graph looks exactly the same. The only way you can tell that this is upside down is because that doesn't read like y equals x cubed anymore, and that's what it says when I hold it right side up. So we call this rotational symmetry, and that's a nice way of testing if you've got it on a piece of paper that you can just flip upside down. A lot of times that's easier to visualize than this mirror image thing that we have right here. So let's just try an example. Let's take an equation and see whether it has this sort of symmetry. Let's say I had x cubed plus the absolute value of y equals 7. And so let's say we're going to suppose that a point xy is on the graph. What that tells me is that x cubed plus the absolute value of y equals 7 is a true equation for that particular x and y value. And so now I'm going to ask, is the point the opposite of x, the opposite of y, on the graph? And so for that, I'm replacing x with the opposite of x, and I'm replacing y with the opposite of y. So I would get the opposite of x cubed plus the absolute value of the opposite of y equals 7. And I'm going to simplify this. If it simplifies to the original equation, which I now suppose is true, then I know that yes, that point is on the graph. If it doesn't, if it simplifies to something else, then it's on a different graph. All right, negative x cubed is just going to be the opposite. I should probably read this as the opposite of x cubed is just going to be the opposite of x cubed, because I'm going to have 3 factors of that negative sign, which is still going to give me a factor of negative 1. Now, what does the absolute value do here? Well, the absolute value is going to get rid of that negative sign. Y and the opposite of y have the same absolute value. That's what the absolute value does. It gets rid of negatives. Now, I don't know whether y is representing a positive or a negative number. I just know that the opposite of y is representing the opposite of whatever y is. But the absolute value of the opposite of y is exactly the same as the absolute value of y. And so if I look, is this equation the same as the original one? No. Because this part's the same, but this part is the exact opposite. So this equation describes a graph that is not symmetric about the origin. So we've got these 3 different types of symmetry that we have, and let's just summarize them. So I've got symmetry about the y-axis. And if that's the case, if I have an arbitrary point x, y, its mirror image would be over here. That would have the opposite x value, but the same y value. I've got symmetry about the x-axis. Most of the time when I have this sort of symmetry, we'll be talking about something that's not a function. And that just says if I have a point x, y, well, where would the mirror image be? It would be down here. So I would have a point with the same x value, but the opposite y value. And then we've got symmetry about the origin, also called rotational symmetry. That's where if I have a point x, y, it's going to look at the origin, see its mirror image on the other side, and that mirror image point, we're going to have the opposite x value and the opposite y value. Now, you could just memorize. If you're checking for symmetry about the y-axis, replace x with the opposite of x. If you're checking for symmetry about the x-axis, replace y with the opposite of y. And if you're checking for symmetry about the origin, replace both x and y with their opposites. I don't encourage you to just memorize that, because I think it's so much easier to think about what symmetry means. Just draw yourself a point. Describe the mirror image. This mirror image has the same y, but the opposite of x. That tells me that that's what I'm going to plug in when I'm testing for that type of symmetry. So what I'm going to do now is I'm going to put 3 problems on the board that I'd like you to try before you watch the next video. And what I want you to do is I want you to check for all 3 types of symmetry. Some equations are going to have more than one type of symmetry. It's entirely possible for a graph to have 2 or even all 3 types of symmetry. And so that's what I want you to check for. So for the first problem, let's say we've got x squared plus y squared equals 1. Check that for all 3 types of symmetry. For the second equation, let's take the absolute value of x plus y equals 2. And for the third equation, x to the 5th minus y squared is equal to 3. So 3 different equations. I'm basically giving you 9 tasks here because I want you to check all of these equations for all 3 types of symmetry. And then tune back in the next video and we'll check out the answers together.